Okay, so the distributive property. It's something you talked about a little bit in sixth grade, and we kind of worked through visualizing what's happening with the algebra tiles. But let's actually talk about and look at kind of how we use it to simplify expressions. So we can right click on here, save to keep, click open a new tab. Then we'll click on it and click again so we get the little pen. And here we go. So first part, we're looking at our kind of formal definition there, right? So the official math definition of the distributive property is this part up here. For any numbers A, B, and C, A, let's make that a little bigger. Okay. A times the quantity B plus C equals A times B plus A times C. And again, times both. If it was further, if it was A times B plus C plus D, we'd have also A times D, etc. there. So you probably use the distributive property whether or not you know it when you do some numeric examples. These ones, not necessarily, but for example, if I wanted to do something like 5 times 13, you could break up 13 into 10 and 3, and those are much easier problems to do 5 times 10 and 5 times 3 and add them together, which is using the distributive property. So looking at numbers here, we know that 3 times the quantity 2 plus 5 means we do 3 times 2 plus 3 times 5. So we'd have 6 plus 15, which is 21. Same thing in the next one. We do 4 times the quantity 9 minus 7, so we do 4 times 9. And then I'll use the same symbol that was in here, so minus 4 times 7. So I have 36 minus 28, which is 8. Again, order of operations, we could also do what's in parentheses first and then multiply. Might be faster in some situations, but I wanted you to see that this is also legit. So algebraic examples that you have here are the same kind of idea. It's just that I have a variable. So the last step where I could put the two together, we won't have that in this kind of problem. So 5 times g, and then I keep the same symbol, so minus 5 times 9. So 5 times g is 5g, minus 5 times 9 is, oops, that looks like a 9. It's a 45. And again, I can't go any further because 5g and minus 45 are not like terms because one has a g and one doesn't. When there's 3 things inside, then you multiply times all 3. So I could do 3 times 2x squared plus 3 times 4x plus 3 times minus 1. So 3 times 2x squared, remember the squared is just what the name of the piece is. So it's just 3 times 2, which is 6x squared, plus 3 times 4x is 12x, and then minus 3 times 1, which is 3. And again, I can't go any further. I can't put those together because they're not like terms. They're different kinds of pieces. If you think of algebra tiles, or they have, different variables with different powers in each one. If this kind of doesn't make sense to you and you're a more visual person, this box method might help you here. So the idea is that you make as many boxes as there are things in the parentheses. You put the number outside on one side and you put the things inside on the other. And so it helps you see what to multiply, right? I do 4 times x, and I do 4 times 3. So I end up with 4x plus 12. So it's a really nice, kind of hands-on strategy if that's something that helps you there. So I could do the same thing in the next one. The 3 goes here. Then I have a 2x squared and a 4x and a minus 1. So 3 times 2x squared would be 6x squared. Oops. Sorry, not super clear there. We got 6x squared. And then we have 3 times 4x, which would be 12x. And 3 times minus 1, which is minus 3. And so there's my answer, 6x squared plus 12x, since it was positive, minus 3. So that's kind of the idea behind that. So whichever way works for you to think about is a good way to solve this here. So in this you do section, what I would like you to do is go ahead and try to pause the video, see if you can do the problems without me, and then we'll come back. Okay, welcome back. Let's check. So in the first one, I have 6 times 12 minus 6 times 2. So 6 times 12 is 72, minus 12 would be 60. In number 2, I have 2 times 4 plus 2 times t. So I get 8 plus 2t. Or if it was an answer choice, we'd probably see 2t plus 8, because we know we go variables before we put the constants in, just like with combining like terms. In number 3, I do 4 times 3g plus 4 times 2. So I get 12g plus 8. And in the last one, I got to do it times all 3 things. So 3 times 5x squared minus 3 times 4x plus 3 times 1. So 3 times 5x squared would be 15x squared minus 3 times 4 is 12x. And then plus 3 times 1 is 3. And so that's your idea that way. Again, can't go any farther with my answer because they're not like terms. The last 2 ones with application are problems that use the distributive property to kind of help us figure out our answer. So it says we have an equilateral triangle. If you throw back to past years, right, if it's equilateral, the EQU tells you that all the sides are the same. So one of them is 4x plus 7. So what's the perimeter of the triangle? Remember, with the perimeter, we go around the outside. So I would add all those 3 sides together. Since they're the same, I really have 4x plus 7, that whole quantity, and then I have it 3 times. There's the distributive property. So 3 times 4 would be 12x, and 3 times 7 would be 21. And that would be your perimeter, since we can't put them together because they're not like terms. Number 2 is one that kind of goes backwards. So it tells you the perimeter, and it wants to know the side length, right? So we needed to be kind of like what happened up here. We needed to say 3 times something is going to equal 12x plus 3. So I know this first thing has to have an x in it, right? So 3 times what would give you 12? That's going to be 4. And then 3 times what gives you 3? That's 1. So kind of going the backwards way, the side length here is 4x plus 1. So again, a different way kind of thinking about it, or seeing the distributive property in action. So we'll go ahead and go back here. We'll put this page in our math notebook. And then use it to help you answer the questions.